In this video, we are going to discuss about instrumentation amplifier. The properties of the instrumentation amplifiers are it will provide high gain and accuracy. Second one, high CMRR. Third one, low DC offset. Fourth one, high stability with low temperature coefficient. Then it will provide low output impedance. So the commercially available instrumentation amplifiers are UA725, then AD624, AD524, AD521. The major function of the instrumentation amplifier is precise amplification of low-level output signal of the transducer, and it is widely used in the application where we required low noise, low thermal and time drift, high input impedance, accurate closed loop gain. Okay, accurate closed loop gain. So first, it is used for monitoring and controlling the physical quantities in the industrial process for measurements and control of temperature, humidity, and intensity. Okay. First, let us discuss differential amplifiers. Yeah. So we have already discussed this circuit. So in that we have taken all the resistance value as the same value. But now I'm going to take it in a as it is. Okay. So first, let me take this one as sweep in the science. So first, if V1 is grounded, okay, if V1 is grounded, what will happen? This is R1 and this is V2, and this point becomes V1 by V1 minus plus. So since this is grounded, these two resistances are in parallel, right? So this is R3 in parallel with R4 and this is grounded. So there is no use in connecting the resistor in this way. Okay, so it is connected to ground only. So what is my value? V0 is equal to minus R2 divided by R1 into V2. That is the answer. Okay. So this is for the first case by applying the superposition theorem. Okay. So next one, I'm going to consider V2 is grounded. Okay, so V2 is grounded. The circuit looks like this, right? R1, R4, R3, and this is V1, and this is, so if I take this point as VA, so what is the value of VA? VA is equal to V1 R4 divided by R4 plus R3, right? So that is my, this is my VA point. Okay, so if I consider the current value, the current is nothing but 0 minus VA divided by 0 minus VA divided by on R1, that is equal to VA minus V0 divided by R2. Okay, so I can write minus VA divided by R1 minus VA divided by R2, that is equal to minus V0 divided by R2. Okay, so I can write, if I take V0 common, I will get R2 R1 divided by R1 R2 is equal to V0 by R2. So here R2 R2 get cancelled. So what is my V0 by VA? V0 by VA is equal to R2 plus R1 divided by R1. And that is nothing but is nothing but 1 plus R2 by R1. Okay. So we know that V0 is equal to VA into 1 plus R2 by R1. So what is the value of VA? VA is nothing but VA is nothing but, this is your first equation. You substitute that equation here. V1 R4 divided by R4 plus R3. Okay. 1 plus R2 divided by R1. So if that is the case, I can take the R4 value below. So I will get like this, right? R2 plus R. So this is your V0. So this is your first equation, and this is your second equation, right? So if I add these two values, since I have used the minus R2 by R1 into V2 plus V1 by 1 plus R3 by R4 into 1 plus R2 by R1. Okay. So if R3 by R4 is equal to R2 by R1, so what will happen if these two get cancelled out, right? So I will get answer as okay, sorry. Let me take this R2 by R1 common. If I take R2 by R1 common, I will get V2 plus V1 1 plus R3 by R4. Okay, into R1 by R2 into 1 plus R2 by R1. Okay, so R2 by R1 minus V2 plus V1 by 1 plus R3 by R4 into 1 plus R1 R2. Okay. Okay. So, yes, R1 by R2 is equal to R3 by R4. If R1 by R2 is equal to R3 by R4, then these two get cancelled out. You will get the answer as R2 by R1 V1 minus V2. Okay. This is your V1. So if the R1 value increases, okay, if the R1 value increases, then that is there is a decreases in the gain, right? In the gain of the amplifier. So this limitation is overcome by these limitation is overcome by connecting voltage follower circuit. Okay, voltage follower circuit at the input of the differential amplifiers. Okay. So let me take that circuit. This is R1. This is R2, and this is R3, R4. Okay. So we know that this is V2 and this is V1. Right. So before that, I'm going to connect one voltage follower. Oh, this is nothing but V1. Okay. So this becomes V1 bar. Okay. And here also I connected one. This one use R bar, R bar. Okay. And here I have connected one resistance, that is R. Okay. This is V. Okay. So I have connected a 2 voltage follower circuit. Okay, this is nothing but a voltage follower circuit. Second, so this point is nothing but your V1, right? This point is nothing but V1, and this is also a V2, right? So this point is V2. So I can write, so the current flowing through this one is, you can write V1 minus V1 bar by R bar, that is equal to I. Okay, so I can substitute V1 is equal to I R dash plus V1 dash. V1 minus V1 bar divided by R bar is equal to minus I. So if I consider the current is flowing in this direction, okay. So then I can write this is minus, so minus I1 R1, okay. So I can write V1 bar is equal to V1 plus I R dash, R1 dash, okay. Okay. So next, if I write the current is flowing in this direction, okay. So I can write V2 minus V2 bar by R dash is equal to I. So I can write V2 minus V2 is equal to I R dash plus V2 dash. Okay. So V2 dash is equal to minus I R dash plus V. So this current is nothing but I that is flowing in this direction, okay. So this is nothing but this is your current. This current I can write it as V1 minus V2 divided by R, okay. So you substitute in this two equation. This is your first equation and this is your second equation, okay. So V1 dash is equal to V1 plus V1 minus V2 divided by R dash. So V2 dash is equal to minus V1 minus V2 divided by R dash plus C. Okay. So we know the formula for this one. So what is V naught? V naught is equal to R2 by R1. And here it is given as V1 minus V2. Okay. V2 minus V1. So I have taken as V1 minus V2 here. So you have to consider V naught is equal to R2 by R1, V2 minus V1. Okay. So V naught is equal to R2 by V2 dash minus V1 dash. So now you substitute the value R2 by R1, V1, V2 by V2 plus V2 minus V1 R dash by R minus V1 minus V1 minus V2 by R dash. So this I can write as R2 by R1 into V2 minus V1, right, plus V2 minus V1 R dash by R, 2 R dash by R, right. So this I can further reduce that as 2 R dash by R. This is your final equation. So here you can see this R is nothing but a variable resistor. Okay, variable resistor which will if it is varied, the gain of the instrumentation amplifier is varied. So far we have discussed about the instrumentation amplifier using three op amps, and this is the output what we have got. And next we are going to discuss about the instrumentation amplifier using transistor bridge. So here this is nothing but resistive transducer. Okay, and here I have given a DC power supply, and this RT as a resistance of the transducer, and del R as a this is nothing but a plus or minus. Okay, del R is a change in the resistance of this resistive transistor. So this is nothing but a resistive transducer. So the total resistance is RT plus del R. So if I want to find the voltage across this terminal, so I can apply the voltage divider rule. By applying a voltage divider rule, I can write VA is equal to V is a total voltage into RA divided by RA plus RT plus or minus del R. Okay. So similar way I can write VB as VB is equal to V into RB divided by RB plus RC. So initially there is no change in the physical quantity. So I can write I can consider the circuit is balanced. So the VAB, okay, the difference in the voltage VAB is equal to 0. So I can write VA minus VB is equal to 0. I can expand this one like VA minus VB. So if I substitute VA and VB, that is here VA is equal to VB, right? So VA is equal to VB. Since there is no change in the RT, okay, so this V and V get cancelled out, and if I bring this RA, if I divide the whole term by RA, I will get 1 divided by 1 plus RT divided by RA, that is equal to, if I divide whole term by numerator and denominator by RB, I will get 1 divided by 1 plus RC divided by RP. Okay, so bringing this denominator to this side, and this also to the right hand side, I will get 1 plus RC divided by RB is equal to 1 plus RT divided by RA. So I can write RC divided by RB is equal to RT divided by RA. So this is the condition for the balanced bridge. So this is nothing but Wheatstone bridge. So whenever there is a change in the physical quantity, the resistance of the transducer also changes, which will causes the bridge to unbalance. Hence, the output voltage of the bridge function is a function of change in the resistance of the transducer. So let us consider. So if we see, since RT is connected across this side, you can see, since this only resistance get changed, and you can see always the VB is fixed, right? So VA only it is changing. So now I can write this VAB, that is equal to VA minus VB, right? And RT is nothing but plus or minus RT plus or minus del R. Okay, so if I take RA, RB, RC and RT is equal to R, and if I take V common, I will get R divided by 2R plus or minus del R minus R divided by 2R. So here the R and R get cancelled out. So on solving this, taking LCM and solving this one, I will get V into 2R minus 2R. This is nothing but plus or minus, right? So plus or minus del R. So we'll get the output as plus or minus del R V divided by 2 into 2R plus del R. So here the 2R value is much greater than this del R. So this will get cancelled out, and I will get VAB is equal to plus or minus del R V divided by 4R. So So I'm going to, this is my input stage. Okay, so this is my input stage. Okay, that is the resistive transistor that is connected to the instrumentation amplifier. So in this, I'm going to remove this, and we know that for this one, the output is V naught is equal to R2 divided by R1 into 1 plus 2 R bar divided by R into V2 minus V1. So if I remove this resistance, okay, if I remove this resistance and these two resistance, I'll get, so what I will get only this output. Okay, right, R2 divided by R1 into V2 minus V1. So what I'm going to do, I'm going to remove this resistance. Okay, and instead of V1 I'm going to substitute VA, and instead of V2 I'm going to substitute VB. Okay, so if I substitute, I will get R2 divided by R1 into VB minus VA. VB minus VA is VBA, right? So I can write V naught is equal to minus R2 divided by R1 into VAB, and so VIB is nothing but plus or minus del R V divide by 4R, right? So this is my output. So here the transistor we are using is nothing but a thermistor which is having a negative temperature quotient or positive temperature quotient. That is negative temperature quotient means if the temperature increases, the resistance get decreases. For the positive temperature quotient, if temperature increases, the resistance also increases. And here the del R is the temperature quotient of the resistance. These type of circuits are used in the applications such as temperature indicators, temperature controller, light intensity meters, and analog weight scale.